be here. And I was asked by Francisca to give a talk here about sort of the computational stuff that we're doing. And Francisca already gave a talk about computational stuff. And then I came in and said, well, we thought you would talk about the solar system. I said, well, I thought I would talk about the computational stuff. So I changed it last minute to the solar system. Because I thought it actually more fun than computational stuff. Even though you need computational stuff to understand something of the solar system. Anyway, this is a picture of the solar system which you will recognize. The inner planets, they're not important. I mean, you can have fun here, but you know, they're really not so much to do about. So I left them out. You have to look at how this works, right? All this technological stuff I'm not so good at. So the inner stuff is left out. We started with Jupiter, and if you look at the solar system from outside, the only thing which you would recognize is probably Jupiter. Jupiter is the only planet that you basically can see from outside the solar system. Saturn, maybe, if you're lucky. Uranus will be completely invisible. Neptune, what Francisca talked about, and the Kuiper Belt will be invisible. And how can you see that this is an American picture?
Because it has Pluto.
What?
Because it has Pluto.
Because it has Pluto, yeah! The Americans like Pluto. Why do the Americans like Pluto? Because they discovered Pluto. That's not a planet, we know. It's a bright planet, it's a Kuiper Belt object. The nice thing of Pluto is just part of this Dutch astronomer, you know, Kuiper, who discovered the Kuiper Belt. And then it sort of stops, the whole solar system. So the funny thing with the solar system is it stopped after the Kuiper Belt. That's what we thought a few years ago. Now, how solar systems are formed, you all know, is in these sort of gaseous structures. And here you see the star formation in action. Really, stars are formed. This is sort of the cradle of star formation. And planets are formed there as well, and maybe even planets with life. Even though it will take a few billion years before the life will realize it's alive. Just like we are realizing that we are alive. But the funny thing about the solar system is this. This is a picture of the solar system, as we had before. These are the inner planets. Now I put in the Sun, the inner planets. Mercury, Venus, Earth, Mars, Jupiter, Saturn, etc. Do you have a movie?
Yeah, but it's working there.
It's not working. It's
It
working.
is working.
Ah, now it is. So you move out of the solar system. And if you move out of the solar system, you see the asteroid belt, you see Pluto, you see the Kuiper Belt, and then there's this funny thing, which is detached from the solar system, which is very small inside. And then if you travel a long way, you get to another famous Dutch astronomer, the Oort cloud, which is here on the edge. But the funny thing is this little object. This little object is called Sedna. And there are even books about astrology written about Sedna by now. Even though Sedna was discovered in 2003, very recently. And it's an object that doesn't really belong to the solar system and doesn't belong to anything else that is not the solar system. So you can wonder, what is Sedna then, right? If it's not the solar system and it's not anything else, it's sort of a unique object in its own. And that's why it's interesting to study. If you study physics, or if you study astronomy, or if you study astronomers, my wife is studying astronomers, well, then you will see that objects which are not belonging to anything else than your group are very interesting to study. So Sedna is worth studying. Now, I come back to the solar system and to Sedna, and one thing which you may not realize is that the story what we need for Sedna is that the solar system has a high abundance of aluminum-26 and iron-60. And that means that the solar system has been very close to a supernova early in its evolution. Now a supernova, as you know, is a star that explodes. And stars that explode are generally very massive, much more massive than the Sun. Now the Sun is one solar mass, and we call it 1. But if you look at a star that is exploding, then you need 10 times as massive a star. So you need a 10 solar mass star, give or take. And here it says 15 to 25, and that is if you look at the amount of abundances of aluminum and iron, you need about a 25 solar mass star. So these stars are very rare. It is like if you look at a crowd like this and you look at an old granny sitting around, and there is none, as I can see from here, and they're not here because they're very rare too. And like very massive stars, they only occur in 1 in 1,000 stars. So very massive stars, like 50 to 25 solar masses, only occur in 1 in 1,000 stars. So if such a star was close to the Sun, you can think maybe the Sun was in a crowd with about 1,000 stars. And that's how you can estimate sort of the size of the cluster in which the Sun was born. So the Sun was not born alone, but the Sun was in a cluster of stars, maybe 1,000, because we had this abundance, we have this abundance of aluminum and iron in the solar system. And this stuff can only be made in the supernova, and the supernova can only occur in massive stars. So you see the circular regulation? Very easy. Astronomy is very easy, right? So the stars explode, leaving a neutron star. The neutron star is gone, being kicked out of the stellar environment. And where are now the siblings of the Sun? And what are the consequences of having the siblings of the Sun around? Now, you can ask a few questions, and already asked a few. How many stars would there be in this cluster? What is the size of the cluster? Where in the galaxy were we born? I mean, you know maybe that we are orbiting the galactic center, and an orbit takes about 250 million years. That means in the 4.5 billion years we have made about 20 or 30 orbits around the galactic center. So were we born in this side of the galaxy or at the other side of the galaxy? It all has to do with Sedna, it all has to do with this birth cluster of the Sun. And where are all these siblings now? Which we don't know. Can we find them back? Is an important question. And we're looking for it, but we don't know the answer yet. Now if you look at the birth environment of the Sun, this is how a birth cluster of the Sun looks like. There's some gas around, that's the stuff where stars are made of. And there is this clump of stars where all the action is taking place. So all the stars are in this little clump, in this cluster, and they move around. They have all their little planetary systems. Each star has its little planetary system. And the stars are not static on the sky, but they move around in this cluster. I think I get a movie now.
Yeah.
See? Movie. And it's the same movie that Francisca showed. This is a star cluster, which we simulated. And you see the stars moving around, and I'm not interested in supernova right now, which are these billiard balls. But the fact that the stars all move around, and they interact with each other. So the stars, when they move around, they may get close together. And if they get close together, they may maybe doing something to each other's planetary system. If another star would pass the solar system very closely, it may perturb Earth's orbit. And it would not be good, right? Because Earth's orbit is just right. I like Earth's orbit. But if the orbit of our planet is changed, we will be in trouble, right? And that's the same thing that will happen here. So you can wonder, if this happened in very much past in the solar system, and Earth's orbit is nice now, maybe it wasn't so nice in the past. Maybe another star passed by the solar system and changed the solar system as it is today. So in the past the solar system was different. And then you can ask the question, can you calculate what the other star, if there was another star, has done to the solar system? Oh, I'll take a sip of my beer, because you were doing that too, right? Cheers! Thank you. So the question is, can you derive something in the solar system of its past, dynamical history, like what happened when the Sun was born in a cluster? And the answer is, of course, yes, you can, but it's not that easy. Can you kill the movie?
Yes, I can.
So my grad student kills the movie. Very nice. So you can come to a realization that, okay, if you have stars around and the stars interact with each other, and the star passes very close, if it really passes very close, it would destroy the whole planetary system, and our Earth will not be in such a nice orbit anymore. And we know that that didn't happen because we are standing here. Most of you are sitting here, right? So the star didn't pass very close. It didn't pass very wide, maybe, because if it passes very wide, it would not perturb the solar system at all. So there is sort of a Goldilocks area where the star may pass close, but not too close. And that is depicted here. This is the distance of the encounter, and this is the eccentricity, let's say the ellipticity of the encounter. How elliptic was the orbit when it closed, when it passed by. This is the perturbation of Neptune, that is the outer planet, and we know that everything inside that orbit has been perturbed by the planetary systems. Planets scatter around and they do all kinds of things. So any orbit you find inside the orbit of Neptune, I cannot deduce anything back from the early solar system because everything will have changed. But orbits which are outside this region, I can use as a diagnostic in order to understand something of the early solar system. And there are two objects there. One is Sedna, and the other is 2012 VP 113. Sedna was discovered first, and VP was discovered later. We just call it VP, right? Sort of a nice name for VP. So you see they're outside the influence orbit of Uranus and Neptune. This is Neptune's influence orbit, Uranus orbit will be inside here. And what you see here in the color bar is the probability that another star passed the solar system within that distance. And what you see here is that the sort of the blue-greenish area, which is here, is where the blue-greenish is where the logarithm is 0, so the probability becomes quite likely that another object passed the solar system at that distance. So my claim is that these orbits, which you see here, are affected by stars, which we don't know which they are. Right? They're affected by something in the galaxy, and we cannot trace back that object. So these stars, these planetaries, the planetesimals, because they are planetesimals, or dwarf planets, are affected by other stars in the galaxy in the early history of the solar system. So they're sort of a time machine for the astronomers to look back in the earliest history of the solar system. I think that Sedna and 2012 VP 113 are the relics of when the sun was born in its star cluster. And I can demonstrate that, how that works. Aha, movie. We have a second movie, and in the movie you see, can you stop with the movie? Can you kill the movie again?
Okay.
Santiago. Yeah, track the movie, no, here, yeah, here. So, I was a bit too quick. So when the sun was in the star cluster, if, let's say, this is basically a three-body problem. You have the sun, somewhere here, right? This is the sun. And the sun. You have Sedna, and it's basically a three-body system. There's another star. Let's assume that Sedna belonged to another star in the past, and the other star passed the solar system very closely. And the sun stole Sedna from the other star. And like the Entvoerung aus dem Zerei, but here we, capture Sedna. They're singing downstairs, they're singing Sailorman songs, So there is another meeting here downstairs. If you want to sing Sailorman songs, it's a women's group, and they are longing for men to also sing along with some Sailorman songs. Yeah, it's true. So, if Sedna belonged to another star, and the other star passed the solar system in the earliest history of the solar system, and the sun stole Sedna from the other star, then we can use Sedna to trace back the orbit of the other star. And the reason is that this is all classical mechanics. Newton knew already this. Newton was thinking already that stars may be able to exchange material. And Sedna may be exactly the object is doing that. So we tried to do that together with Lucy Yilkova, and we set up a computer model of the two stars and Sedna around the other star, passing the solar system, and seeing what is the most likely sort of orbit that the other star would have had in order to capture Sedna. Well, that we would capture Sedna from the other star. So the other star has a disk. That's what you're going to see in the movie. Yeah, the movie.
Okay.
There we get a movie. Santiago makes a movie. This is the sun. And the blue thing is this. This is the other star. And the red stuff is this. So these are all kinds of potential Sedna-like objects. And how you see how material is exchanged between one star and the other star. So the orange stuff here belongs to the red star. That's us. Okay, what did you do? There we go again. Sun, the other star, and we exchange the blue stuff to here, and that will be the Zetitos. And you see that there are many objects which are called orange here, well, colored orange, and they get into orbit around the sun. And the orbit they have is consistent with the orbit of Sedna. And the fun thing is, as you see here, if the other star did not have one object but a whole bunch of objects, you may be accreting, stealing, maybe 1,000 objects, maybe even 2,000 objects from the other star. There you go again, get into repetition. So you see all these 1,000 objects getting to orbit around the sun. So the prediction is, from this model, that there are about 1,000 objects like Sedna in the solar system. Now if you look at the right part of that movie...
You want again?
Yeah, let's do it again. Here you see the orbital elements. This is the disk of the sun, this is the distance to the sun, and this is the ellipticity of the orbit. It's 0 at the beginning, And this is how you see that the orbits are perturbed by each other. The blue stuff is our own, so that gets scattered around. And the orange stuff is stolen from the other star. And I can tell you, if you can see the movie again. Thank you, Francisco. That Sedna will be about here. Sedna is about this dense part. And that's not an accident, of course. This simulation is made such that Sedna would be reproduced by this simulation. Yes, thank you.
Yeah.
Thank you. Now, the idea is now that we have sort of a parking zone in the solar system. Inside this line, here is the semi-major axis, the distance to the sun. And here is the electricity. That if the distance to the sun is very small, we cannot say anything, because everything will be perturbed by the planet, everything is scattered around, it's a big mass, basically. The area where the Earth is, it's a big mass. And then there's an area where the star cluster will not have penetrated its influence, that's what we call the frozen zone. There's an area where the star cluster has influence, but the galaxy itself has no influence, and that's what we call the parking zone. And Sedna is exactly in this parking zone. And we think there are about 1,000 objects like Sedna ready to be discovered. I think that's yeah, I can flash it, right?
Yeah.
And I say here that the sun was born is about 1,000 stars, 500 are that's the same, right? I mean, 1,000 stars. Within a parsec or so, there was a supernova nearby that enriched the cluster, therefore we know that it was a cluster. We had an encounter with another star, I didn't tell you, but it's about 1.8 solar star. So it's a bit more massive than the sun. We had about 1,000 Sedna-like objects in the solar system, but only 2 are known right now. Actually, there's a dozen known, but we think there's 1,000. And this approach was very, very close. The star passed the solar system, it almost hit the solar system. In astronomical terms, this would be a clear hit. If you just got Sedna from it. The fun thing is that the other star also stole some objects from us. It would be very nice to find back, because then we can say to the other star, can you get our stones back? You can have Sedna, and we want to have our own stones back. And that's all.